So hi everyone, I'm Martin, I'm from the Bluetooth Special Interest Group. We're actually a standards organisation, but we are the company behind Bluetooth technology. As for me, I'm a technology professional and working in various roles in software development and communications technologies is all I've ever done. Still love coding, and I write software for all sorts of platforms, including mobile and embedded platforms. Anyway, thanks for attending today. As you know, last year, early in 2020, the world changed when we found ourselves in the middle of this global COVID-19 pandemic. And here we are in 2021, and we're still dealing with it. Now, you're probably aware that various applications to help deal with COVID-19 in various ways have materialized, and many of them use Bluetooth. So I'd like to talk about this and share what I know about the technical aspects of Bluetooth as used in many of these applications. In particular, I'll talk about exposure notification systems and the framework that was created by Apple and Google for ENS applications. I'm not a spokesperson for either of these companies, of course. I'm just an interested technology professional with some knowledge to share, no more than that. So last year, we at the Bluetooth SIG started to become aware of companies and individuals from the technology sector who were thinking about the pandemic and ways in which technology might perhaps be applied. And I had a few conversations at this stage with people wanting to know more about Bluetooth to see if it had the potential to be one of the technology ingredients of various ideas. And those ideas seem to fall broadly into three categories: ways of helping with social distancing, exposure notification systems, which is what I'm really going to talk about today, and large-scale contact tracing systems, which involve technology, but also people and manual procedures and things like that as well. So ENS is our topic for today. So what exactly does an ENS system do? Well, an exposure notification system is concerned with identifying occasions when you may have been exposed to a person with COVID-19 symptoms or who has a positive test result. And we call such people affected people. It involves detecting the presence of other people in the environment and estimating the distance from you to each of the others, because how close people get to you is one of the most significant risk factors. So knowing how close you've been to individuals and for how long allows the system to then notify you that you may have been exposed to the virus if it later transpires that one of the people you encountered is an affected person. Now, it was clear from very early on that smartphones and Bluetooth were very frequently being considered for use in these kinds of solutions. And smartphones, because they're in widespread use, not everyone has a smartphone, but many do. So taking advantage of them has obvious appeal. And Bluetooth was of interest because it's a wireless communications technology that smartphones support, and it requires no infrastructure. So there are no access points to deploy, no routers, no radio masts, nothing like that. Communication takes place between devices directly. Now, be aware that early in 2020, when ideas were first being discussed, my organization, the Bluetooth SIG, had no formal role in any of this. We were just interested observers watching what people were coming up with. And furthermore, back then, Bluetooth itself had no specially designed standard capabilities for use in applications like exposure notification systems. So it was really very much a case of work with what you've got, leverage the existing capabilities of Bluetooth somehow to create solutions. So what are those basic capabilities or raw ingredients? Well, first of all, two Bluetooth devices can form a connection and exchange data over it. This is a very reliable way of using Bluetooth because timing parameters are agreed by both devices. Data can be encrypted for security, and there's a privacy mechanism that disguises device addresses so you can't be tracked using addresses transmitted in packets over the air. But scalability is quite limited, especially on smartphones using connection-oriented communication. Typically, a smartphone can only accept 3 or 4 connections from other devices at a time. So with ENS in mind, imagine walking into a supermarket on a busy day. There might be 100 other smartphones you need to exchange data with. So connection-oriented communication is not a great fit with basic ENS requirements. Connectionless communication, on the other hand, involves a device broadcasting data. So this means transmitted packets can be received by an absolutely unlimited number of listening devices in the environment. So it's extremely scalable. There's no standard encryption mechanism for use with connectionless communication in Bluetooth, but the address disguising privacy mechanism can be used. Now, a transmitting device transmits a signal with a certain amount of output power, and we call this the TX power. The receiving device can measure the strength of the received signal, and we call this the RSSI, or the received signal strength indicator. And the RSSI value gets lower the further the receiver is from the transmitter, and this, of course, can be quite useful. Now, the way in which the RSSI decreases with distance from the transmitter is not linear. In fact, it follows an inverse square law. And if you know what the TX power used by the transmitter was, you can subtract the RSSI value measured by the receiver from the TX power to obtain something we call the path loss or attenuation. And this can then be used in a path loss calculation to estimate the distance between the two devices. So armed with these raw ingredients, this is how an exposure notification application can work in simple terms. So imagine once again several people in a supermarket, all with an ENS application on their smartphones. So each device will periodically broadcast a unique ID and the value that represents the transmission power level being used. So this is called beaconing, and it's a way of saying I'm here to the other devices in the shop. The other devices receive the broadcast information and can then use the RSSI and TX power values to estimate how far away the broadcasting device is. Now, each device interleaves broadcasting beacons containing its own unique ID with listening for beacons from other devices. And they collect details of the devices that they've encountered with each such event known as a sighting. Then users who develop COVID-19 symptoms or maybe have a positive test result voluntarily disclose their status. And then the system arranges for everyone that's been near to the affected person to be notified that they may have been exposed to the virus. So that's the essence of how these systems work. But what I just described was a very naive, very much simplified description. There are all sorts of technical challenges if you want to make an ENS system using Bluetooth that's truly effective. So let me walk you through some of the key issues now. So using the received signal strength to estimate the distance between a transmitter and a receiver doesn't yield particularly accurate or even consistent results, but it can be made to work well enough anyway to be useful if you take the right approach. In particular, it can only work if you're basing your calculations on a received packet that contains the transmission power that was used as a data item in that packet. You have to be able to subtract the signal strength measured at the receiver from the transmitted signal strength to determine the path loss and then estimate distance. Without knowing the transmission power that was originally used, any calculations you do just using the received signal strength are quite meaningless. Now, where ENS systems are concerned, we're interested in cases where users are relatively close to each other. And luckily, estimates of distance are better when devices are closer because of the inverse square relationship between signal strength and distance. As you can see from the chart, the change in RSSI is much larger for a given change in distance when the receiver is fairly close to the transmitter than it is when the receiver is further away. So that works for us in the context of ENS. So RSSI is key to estimating distance, but the old saying of garbage in, garbage out applies here because RSSI measurements are noisy, meaning the measurements reported in apparently stable conditions will vary somewhat. Excuse me. And on screen, you can see a plot of real data I captured from a Raspberry Pi sitting on one side of my desk, reporting the signal strength of packets received from a transmitting device over on the other side of the desk. Issues like humidity, the orientation of your phone, the precise radio frequency being used, and the antenna design, these things can all affect the RSSI value reported. And importantly, different models of smartphone may report different RSSI values under exactly the same conditions. So consistency across models can be a challenge. And there are tens of thousands of smartphone models out there. Now, clearly calibration is the answer to this problem, and I'll get to that later. So privacy is a type of security issue where attacks are concerned with establishing patterns of user behavior over extended periods of time by capturing transmitted data and using it to track the movement of devices and by extension their users. That's what we normally mean. And any static or only occasionally changing data transmitted by your phone constitutes a privacy risk. And this applies to any wireless communications technology, by the way, not just Bluetooth. Now, here's another issue. Bluetooth broadcasting, the connectionless approach, involves a procedure called advertising. Now, when advertising, small packets of data are transmitted regularly, and how often they're transmitted is called the advertising interval. Devices that are listening for advertising packets perform a procedure called scanning, and how often they scan is called the scan interval, and how long they scan for is called the scan window. Now, advertising doesn't use much battery power, but scanning can, depending on these parameters. And you have to think about how quickly you want an advertising device to be detected by scanning devices, and usually balance that against the need to not use too much battery power. Now, surprisingly, the standard Bluetooth APIs on iOS and Android can themselves be an issue. On the one hand, obviously, they make it possible for us to use Bluetooth from our applications. That's what they're for. But on the other hand, they also limit us, either because there is no API that lets us do what we want to do with Bluetooth, or because the operating system enforces rules about when APIs can be used and how behaviors perhaps vary when your application is in different states, like in the foreground versus in the background. Of course, API availability and device behaviors can also vary across OS versions too. Now, there are two competing architectures to choose from when building an ENS system, and you may have heard of them because one of them is definitely controversial. And the two choices are called centralized and decentralized. Now, the centralized architecture is built around a cloud-based service run by a government public health authority. Devices detect encounters with other devices by receiving device IDs in Bluetooth advertising packets, and they report details of every device they encounter to the central server, which accumulates a large database of every sighting made by every device. Now, COVID-affected users must declare their status to the server, and the central server then evaluates its database and makes all of the decisions about which users to notify if it seems that they may have been exposed to an affected user. With the decentralized approach, users still have to report to a public health authority when they have symptoms or a positive test result, but that's where the similarity with the centralized approach ends. Because periodically, all devices download the IDs of those devices that have declared themselves affected by COVID. And then all processing and decision-making takes place locally on those devices. They simply compare the affected device IDs downloaded from the Public Health Authority server with the list of devices that they've encountered and apply a risk assessment algorithm based on duration of sighting and distance estimates to decide whether a significant exposure has taken place, and if necessary, notify the user of this. So given all the issues, and in particular the need for consistency across the thousands of models of smartphone, and the constraints and the variability of Bluetooth APIs across OS versions, Apple and Google collaborated quite early last year to very quickly create their ENS framework. And since they created it, it's not constrained in what it can do in the same way that the public APIs for Bluetooth are. And so Bluetooth can be used by that framework in exactly the way it's required to be used. It's got some very interesting features as well to provide data of as good a quality as possible to ensure different devices report consistent data and to protect the user from privacy risks as well. And it's a framework, meaning that an application that uses it is still needed, but this allows risk assessments using the ENS data to be made using the particular thresholds adopted by governments in each country, rather than there being a one-size-fits-all approach. Source code for full example applications that use the framework has been provided too, so my guess is it's been quite easy for different countries to adopt the framework. And the first thing to know about the Apple Google ENS solution is that it uses the decentralized architecture. So there is no centralized database of all encounters between devices. Users do have to declare their status to a public health authority server, but that's done anonymously using an encrypted identifier that I'll say more about shortly. And according to their FAQ, Google and Apple do not monetize any of this data. So not surprisingly, the framework uses Bluetooth in a connectionless way because this is very scalable. It's perfect for this use. Devices broadcast a unique ID repeatedly, and they keep records of the IDs that they receive when scanning, along with the signal strength. And so they build up a kind of history of device sightings. So what data is being broadcast in ENS beacons exactly? Well, on screen is a Bluetooth advertising packet that contains an ENS beacon. This is what we call a non-connectable advertising packet, and this indicates that it's not an invitation to other devices to connect. Bluetooth uses a system of service identifiers, and the service UUID of hex FD6F has been allocated to identify the ENS service, and this is how scanning devices recognize that this is an ENS beacon. In another field called service data, we can see the ENS advertising payload. And it consists of an identifier called the rolling proximity identifier and a field called the associated encrypted metadata, which contains some protocol versioning data and the all-important transmit power reference value for use in path loss calculations. Now, advertising is performed 3 or 4 times a second. Scanning is opportunistic, meaning that devices fit it into their schedule when they can, but generally it's happening around once every 5 minutes and lasts for around 4 seconds at a time. Now, obviously, estimating how close 2 devices have been is an important part of any ENS system. So Apple and Google have taken steps to improve distance estimation using signal strength values and to ensure results are as consistent as possible across different makes and models of smartphone. And they've published a calibration procedure which manufacturers are expected to perform, and they report the calibration results back. And there's a CSV file actually containing calibration data. It's got like 10,000 rows in it for each smartphone type, and that gets downloaded by the ENS framework to every phone. Calculations then take into account the calibration data to ensure that results are consistent. And the way the sort of sampling of data works, there's some averaging performed as well, and that smooths the distance estimations, which of course is good given the noisy nature of RSSI readings. So let's talk about security now. The Apple Google ENS framework includes a cryptography specification, and I've summarized the main points here on my slide. So all devices generate a 1 to 8-bit random number called the temporary exposure key, or TEK. It's then used with a key derivation function called HKDF to generate 2 distinct security keys, the RPI key and the AEM key. The RPI key is used with the AES algorithm to encrypt a fixed string value plus a number called the EN interval number, and this gives us the RPI, or rolling proximity identifier. But what's this EN interval number? Well, the way the system works is it divides time since the unique epoch of midnight on the 1st of January 1970 into 10-minute slices, and each slice is numbered. So the EN interval number is the counter number for the current 10-minute period. Now, the RPI value itself is used along with the AEM key to encrypt the TX power and protocol metadata using AES in counter mode. So let's see how privacy concerns have been addressed. Now, as you will recall, there are two sources of potential problem. There's the device address itself, which is used by Bluetooth in advertising packets, and there's the data in the ENS payload. So encryption of broadcast data is ultimately rooted in the temporary exposure key that's in use. This gets regenerated every 24 hours, and the keys from the last 14 days are retained on the device. Now, every time a new tech is generated, the corresponding RPI key and AEM key are also regenerated. But the data actually broadcast over the air is regenerated every 15 minutes. And don't forget that generation of the rolling proximity key includes the current 10-minute interval number. So RPI will change every time it's regenerated. And RPI is also used in encrypting the metadata too, so that's also changing every 15 minutes. Now, Bluetooth itself has its own privacy safeguards, including a device address type called a non-resolvable private address, which the Bluetooth stack changes periodically. And in the Apple Google ENS framework, the Bluetooth advertising address is changed at exactly the same time that the RPI and AEM data is rolled. So you can't deduce anything about one set of these values when the other set changes. Now, when an affected user voluntarily declares their status, their temporary exposure keys from the last 14 days are uploaded to their public health authority server anonymously. And these keys that have been uploaded by affected users, they get known as diagnosis keys, and periodically devices poll the server for the latest diagnosis keys, which they then download. And they then attempt to decrypt the rolling proximity identifiers of devices they've encountered and made a note of locally using each of the downloaded keys. So if they're successful, this means that the user has encountered another person who has at some point become an affected user. The application using the ENS framework then applies some local risk management or risk assessment criteria involving distance estimation and encounter durations, and if necessary, notifies the user that they may have been exposed. And again, all of this is happening on the local smartphone only. Okay, so hopefully I've given you a solid understanding of how the Apple Google ENS framework works and Bluetooth within that. But what about the future? It's it's terrible to think about, but I guess this is probably not the last pandemic, and of course the current one is not yet over, and it makes sense to be prepared anyway. So is there anything we've learned or are working on that might help in the use of Bluetooth technology in this kind of scenario in the future? Well, one thing I can tell you is this. Last year, the Bluetooth SIG established a working group to study this subject and to look for opportunities to improve or standardize how Bluetooth can be used in exposure notification systems. In particular, of course, it was noted that not everybody has a smartphone, and that in fact some of the most vulnerable groups of people don't. So one of the key ideas that's emerged is to allow relatively cheap wearable devices like bracelets to be issued to people, and for the wearables to perform the same kind of beaconing and data collection activities that I've described. The wearables could then periodically upload and download data from the internet via a smartphone that they've been paired with. So the expectation is that at least one member of an extended family or support group has a smartphone, and everyone else, young and old, can be issued as one of the small wearable devices. So in this way, more of the population can be protected. And in fact, in Singapore, they were clearly thinking about this along the same lines, because their population were issued with small tokens which serve this very purpose. Okay, let me leave you with some pointers to resources on this subject that you might find useful. So here are 3 websites that contain ENS information from Apple, from Google, and from the Bluetooth Special Interest Group, respectively. And that's for general Bluetooth technology information for developers. Bluetooth.com is, of course, the place to go. That's our website. And we have quite a nice collection of self-paced, self-study resources we call study guides. They each deal with different Bluetooth topics. Between them, they cover a whole range of different platforms too. So they all contain hands-on project work as well. So if you're like me and you learn best through doing rather than just reading, you'll probably like them. The most relevant study guides to ENS are the first 2 on the list on my slide there. We've also got all sorts of papers. They're often a quick way to learn about a subject, none of which is a substitute for our formal specifications, but they do make the learning curve less steep. So that's it. Thank you so much for listening. I hope that was useful. There should be time, of course, for some questions in a moment. But I'm on Twitter as well, so feel free to get in touch if you need to follow up. Thank you once again.
Well, thank you, Martin. That was very cool to see how the whole exposure notification system works. So what does the future of Bluetooth hold? Like, what can we expect?
Yeah, it's a good question. It's a question I always struggle to answer in a way because yeah, I'm not allowed to tell everyone what's going on behind the scenes necessarily, so I always get in trouble for this. But I'll tell you what the hot topics are anyway, some of which is in the public domain already, but the things that get me most excited are still Bluetooth Mesh, which is a couple of years old now, but Bluetooth Mesh lets you create quite large networks of smart devices, up to 32,767 to be precise. It's designed really for things like smart buildings. Have to be precise. I'm a geek, you know that. So it's designed for things like smart buildings where you want the building to behave in a very energy efficient way, for example, so sensors are informing other systems in the device and they're automatically adjusting levels of lighting and heating and things like that. It's very cool technology. It's being widely adopted as well, actually, because it's extremely scalable and very secure. So Bluetooth Mesh is cool. We've got a really interesting location-based technology that's been out for about a year and a half now. Lets you determine the direction that a Bluetooth signal is being transmitted from in 2 planes, vertical and horizontal. So you get 2 lines that cross. Where they cross is a specific location, and it can be accurate to within 10 centimeters. So for indoor navigation, that is quite phenomenal. Cool. We are also working on a high accuracy distance measurement technology as well, which may or may not have some bearing on today's topic. We'll have to wait and see. That one's not really not out there yet. Beyond that, I guess the really hot topic, the one that gets my marketing colleagues really excited, actually is the new audio technology. And Bluetooth has been around for 21, 22 years nearly now. And amongst the very first product types were audio products, and audio is still very, very big. I'm using it right now. Yeah. But this is using the old Bluetooth. And Bluetooth Low Energy is where all the action is these days. And there's a new audio technology called LE Audio. We've released almost all of the specifications for that. There's a big collection of them because it's a whole framework. We talk about the generic audio framework. Not only does it use LE and therefore it's more power efficient, there's a new codec for better quality, but best of all, you can do things you just can't do with the old Bluetooth audio. You can share audio with multiple people, friends. You can broadcast audio to a private audience, maybe in a cinema, who access via a code, or publicly. And you can transmit multiple content streams simultaneously. So you could have the safety briefing on a plane being transmitted in multiple languages simultaneously, and you'd pick one, I'd pick another. So it's a really exciting thing, actually. I think we're going to see a whole new generation of Bluetooth audio products as a consequence of LE Audio.
So in which state does it currently, are there already products being created, or is this just a specification at the moment? Or
they're being created, and I know this because I do a lot of the support for product manufacturers who are in the process of implementing. So the general process is work goes on the technology, and the output is one or more technical specifications that have been agreed. So that's the standardization work, if you like. Lots of companies involved in that, not just us. Manufacturers then have to implement, but those who are involved in the standardization process are doing that alongside the development of the specs. They're not waiting, it's not linear. And then eventually, of course, products appear in the shops for you and I to get our hands on. Almost all of the LE audio specs are out. I know, as I say, for a fact, companies are developing now, because I'm answering some quite tough questions about the subject, actually. Yeah. But it's a sign that there's interesting things going on there.
So when could we expect these things to actually happen? In a couple of years, or?
I think less. It's always really hard to know, because this is now over to the manufacturers and what they perceive the urgency to be, size of the market opportunity, stuff like that. But it's also for hearing aids, by the way. So I don't think there's a standard for wireless hearing aids. So this is a massive market. So I think I'm right in saying that this will be enormous. Yeah. And I think we'll probably see things by the end of the year or early next year. Don't hold me to that, because I have no control over the engineering schedules of the various products. And that's my sense of how things are going there. So we shall wait and see.
Yeah. And also, you mentioned in the presentation that YouTube is very dependent on the range. It seems like this is getting better. Like, I can still connect to devices that are in different rooms. So how is this possible?
The range capabilities of Bluetooth have changed enormously over the years. Back in the beginning, it was like 10 meters, I think. We used to talk about personal area networks. We don't say that anymore. Even as recently as maybe 5 years ago, it was up to hundreds of meters. But then Bluetooth 5 actually introduced a new capability called LE coded, which uses a mathematical technique that comms people will understand. It's called forward error correction. And it allows you to extract data cleanly from very weak signals. So in other words, you can be much further away. And the range these days is easily 1 kilometer using LE coded. And this is like, I always think when I'm saying this, people aren't going to believe me. They'll think it's like a marketing thing. But the fact is that you can see on YouTube companies demonstrating this. But I met a Japanese consumer electronics company last year. They're a household name. I'm not going to name them, but you've heard of them for sure. They told me, it was actually a conference, they were talking about this. They'd measured a range of 3 kilometers. It was on a beach in California. I think I've mentioned this in other talks I've done before, because I'm fairly sure they chose the location because, well, why wouldn't you want to go and work on a beach in California? But 3 kilometers there, which is astonishing. So range has really changed. But what you get in specific products depends on how manufacturers are using Bluetooth and other factors to do with device design that have nothing to do with Bluetooth itself, antenna design and power consumption constraints and things like this. But the potential for very long range is there.
Yeah, and that combined with the fact that you can have Bluetooth meshes, then that becomes very powerful. Yeah.
Bluetooth mesh messages get relayed across the network. You can do it up to 127 hops from device to device. Effectively, messages travel at the speed of sound. So you can create a mesh network that's kind of envelops a very large building or collection of buildings. I know one guy I talked to, they were looking at Bluetooth mesh for a neighborhood solution. So yeah,
that's cool. And how reliable is Bluetooth?
Yeah, I really like this topic. I actually wrote a paper on Bluetooth and reliability last year. It's one of the ones on my list. I think you'll find it on our website. Bluetooth is full of engineering decisions and features that are to do with making communication reliable in the most challenging of situations. And my favorite, and it's fairly unique, I think, amongst the kind of usual suspects, is this. If you're familiar with how your Wi-Fi works at home, you have to pick a channel. You have a selection of channels you can use. When you muck around with your router to configure things, you get to select a channel. Now, a channel is actually a range of frequencies. There's an upper frequency boundary and a lower. And any signal transmitted on a frequency between those two limits is said to be using that channel. Now, if your neighbor is using the same channel, then you may be experiencing problems. Perhaps you complain from time to time that your Wi-Fi is a bit slow today. What's probably happening is that packets transmitted by your neighbor on the same channel are colliding in the air with packets on your network. And any collisions between packets results in corruption. The packets are lost. Devices have to start trying to retry to get the data through. And so things slow down. Best case, they slow down. Worst case, they stop working. So Bluetooth has a concept of channels as well. But with connected devices, there are 37. And rather than use one channel that gets chosen, Bluetooth does something called adaptive frequency hopping. So very often as every 7.5 milliseconds, the two Bluetooth devices choose a new channel. They each know what the hopping sequence is going to be, and they kind of dance around the full 2.4 gigahertz spectrum using the entire set of 37 channels. The probability of collisions from other devices is very, very small now because we're a moving target. And better still, devices are measuring how well each channel performs. If they find that there's consistently interference, say on channel number 25 or something, it gets crossed off the list. It gets eliminated from the hopping sequence. So noisy channels get avoided. So devices optimize and dynamically optimize the way they're using the entire spectrum in their frequency hopping. This is the adaptive part, so that data will still get through even in a very hostile, noisy environment. So it's full of stuff like this. It's some really clever things. Even if you're not a specialist in Bluetooth, a quick look at some of the things in the spec is very informative. There's some really great engineering gone into it.
Yeah, very, very cool. Very interesting. We also, during the talk, asked a question to the audience. Maybe we can check the results of that now. The question was, do you have Bluetooth covert tracing enabled? And let's see, 100% of the people that replied.
Oh, cool.
Yes. So that's a very good sign, I think.
As long as that wasn't just one person, that's good. Yeah.
No, it's 5. It's 5. It's not a lot, so, but
that's still good.
It's good enough.
Yeah.
So for the next talk, we have another question. Are you going to check out Quarkus? And maybe you're not convinced yet, but our next speaker will convince us. For now, Martin, thank you very much for coming on.
You're very welcome, and thanks everyone for listening.
Thank you.